All right, so welcome back. Happy return. This is the continuation, I guess, on polynomial functions and everything to do with factoring. Now, hopefully you'll see why the factoring is kind of useful to know. So I'm going to do an introduction on rational functions, but here the rational functions. So when we have a function in general, so let's say we have our input, whatever that input is. Typically we call it x, but it doesn't have to be. We have our output, and then we have our function, but we will restrict this function, at least for this video, to have a numerator, and I'll call that numerator n of x, and then a denominator, which is going to be d of x, and those are going to be just polynomials. Now, when that happens, then we can try to think, what those functions actually have to have as restrictions, because we know that in denominators, if we set a particular value to x and then the denominator becomes 0, then we run into a problem. So the function is not defined there, so we're going to look for that. But because both the numerator and denominators are going to be polynomials, sometimes we can reduce these particular rational functions and make them much simpler. So we'll do that through a few examples. And when I'm referring to these rational functions with numerators and denominators being polynomials, so what I mean, so for example, you can set, and I'm just kind of making this up, but so a polynomial, for instance, could be something like this, and then the denominator polynomial could be, let's say, something like this. Let's say maybe x cubed plus 4x plus 2 or something like that. And then our function overall becomes f of x is equal to 2x squared plus 1 divided by, and then we have x cubed plus 4x plus 2. So that's what we have, and that's what we mean by a rational function. So rational you should be familiar with because you have run into rational numbers, right? So rational numbers typically are kind of designated as fractions per se. So here when we say rational, we have a numerator and denominator, but we have them as polynomials, right? So when we have these particular functions, sometimes it's very hard to think, how do they look like? We've seen quadratics, we know lines, right? So we've seen numerous parent functions. Maybe I'll put up a link up above into those parent functions so you can explore them again if you've forgotten them. And then, you start combining all of these different things, then how do they look like overall? So, okay, we have a rational function, so we understand that. But then what if, we had to kind of think what values of x are possible here to enter into these, and then what are the possible outputs, okay, into the overall thing. So let's take a look at a few examples, and I'll try to illustrate this and things for you to think about, for example, like restrictions on your denominator. All right, so here's our first example. So it's a little bit easier example that we have, and it's f of x is equal to x over x squared plus x. Now, for this, again, we know that for any function, we cannot have the denominator equal to 0, because if it is, we're going to run into 0 over 0 or a number over 0, and in both cases, we don't really have an output per se. So we want to be able to restrict the denominators in a particular way for all the values of x that it equals to 0, and then it creates a particular domain for us. So I'm going to do that for you in just a second. Now, from all of those factoring of polynomials, we can simplify some of these. So for example, I can write this out as, so there's really nothing to simplify on top, but I can take out my x, so I can factor out my x from the bottom. So I will have the same function, except it looks like this. And from here, now it's very easy to see that, hey, wait a minute, well, we can't have x is equal to 0, because in that case, we're actually going to get 0 over 0. And the other place that we can't have x is we cannot have x at minus 1 right here. So we have a restriction on x. So x cannot be equal to 0, and x cannot be equal to negative 1 from the denominator. And if you were thinking of this as a domain, so then you would set your domain and you can say, okay, so x can be any real number. However, so such that, it has to be restricted. Okay, so these, I'm going to duplicate this and kind of put it within here. Maybe let's shift it over so that we have our domain. So this would have been our domain, and we cannot have x at these two particular values. But because of this factoring in the denominator, well, that's kind of nice, because now notice I can take out the x and the x, and I can simplify this much more, which is 1 over, and this would have been just x over 1. And this is the same thing as our parent, 1 over x. And we know how 1 over x looks like. So, you know, if you recall, so if I have here my x and y axes, so my parent, this, basically looked like that. Okay, so we kind of were shifting this in this particular way, but here we have shifted this over by just that -1, so it's going to move this graph over to this side, right? And that's how the actual f of x would look like, and it has helped us that we would have, okay, this actual factored form. But what we're going to have to be careful with is at these two values, you know, we actually won't have, or won't be allowed to have a value at x, okay, because it's going to be undefined due to the restriction on the actual domain. So let me graph this for you quickly so that you can see what we mean, and I'm going to use Desmos. All right, so welcome back. So notice, okay, so this is what we have, and the, I guess the factored form, I'm going to call it g of x, which is just 1 over x plus 1, and notice they're on top of each other, right? Because we have factored out the x from the top one, and then it just canceled out. However, let me hide this one away. The original one, so the way that it looks when Desmos graphs this out, it looks like there is a value for basically x is equal to 0. But I encourage you, so I'm going to kind of zoom in here, and I'm going to encourage you, okay, so notice what happens. If I come approach this, you know, Desmos is actually going to point out to us that, hey, wait a minute, at 0 here, okay, so as I get closer and closer, right there, notice that there's no point there, and it says undefined. And that comes from that restriction from the denominator. So you can't see it from the graph, but it basically is blank at that particular point. It has values approaching coming in, and it has values approaching from this side, but at that x is equal to 0, we actually cannot have anything there because the denominator would be equal to 0. All right. Otherwise, it basically looks like our parent function 1 over x just kind of shifted over to the left. All right, so that's what happens there. Here is another example that I have for you. So this one is a little bit more complicated, but again, it will show you and give you some kind of an insight on how to think of these rational functions. Now, you may not always be able to factor things out. So sometimes, for example, this one that I plotted within here, because I was just making it up, you know, we can't really factor it in any particular way that might help us so that we could try to make this a little bit simpler. And in those cases, you're kind of stuck, right? So you have a function, which is a rational function, and then you can plot it. Now, because we have Desmos, it's so much easier for us to do it. However, we can still also do it by hand, more or less, to try to estimate it. And, you know, I've done examples with some very hard ones in the introduction to functions. I'll put a link up above to those examples. I kind of tortured you through them in the beginning before you even started rational functions per se. In any case, let's come back to this second example right here. And I'm going to try to do kind of similar tricks here. I'm going to try to see if I can maybe factor anything out. We also want to make sure that our denominator is not equal to 0. So we want to see what restrictions we have to set for our domain. So let's try this. So on top, so right away I kind of see x right there. This is going to be, I guess, x plus 2. So that's factored for the numerator. Now the denominator, I don't know if that's, oh, this is actually a perfect square. So this is x plus 2 squared, right? Because the square root of x is x, and the square root of 4 is 4, and then when you add them up, 2 plus 2 is 4, so that gives us that middle term. So in this case, well, if I factor, so one of these is going to be gone. So this is just going to be x divided by x plus 2, which again is going to look kind of similar, okay, so because we have this right there, to that 1 over x. We do have an x on top, but that 1 over x, okay, we'll see what's going to happen. All right, so how do we, take a look and see as this keeps on going. Okay, so now what are the restrictions here? Because notice that here, our denominator, we cannot have x is equal to -2. So that's going to give us a problem there in the denominator. Now we have 2 of those in there. So our domain, so I'm going to define it x, so it can be any real number, but it is not allowed to be -2, because if it is, then we run into the problem of having an undefined at that particular point. And then the rest, all right, so this is kind of how it's going to look like. So there's something that's going to be happening at -2, right? We're going to be probably blowing up in some particular way. And then as x gets bigger and bigger and bigger, we probably will notice that it's going to start to reach something. And it looks like, because you're going to have x over x right there as x gets bigger and bigger and bigger. So it's going to be +1. And in the negative space, it's also going to be going towards that +1. All right. So again, I'm going to try to graph this for you so that we can see it. Okay, so let's do that using Desmos. All right, so there you have it. Okay, so that's kind of how it looks like. This is what we have. So again, it looks, very, very similar to what we have to our parent function. However, okay, so notice that it kind of looks like it's just kind of flipped around for us, okay, within this particular case. So if we have this, okay, so notice that the problem here is, again, so at -2, it's kind of undefined. So we can't have any values there, but for everything else, it seems to work pretty well. And notice that here, indeed, it starts to approach 1 from the left, and then here it's approaching 1 from the right as well, as you keep going and making it bigger and bigger and bigger. And you will notice that right here. All right. So that's how this one actually looks like. So again, very similar to our kind of 1 over the x plus 1, almost. All right. Here's the last example that I have for you. So again, in terms of rational functions and just kind of thinking about trying to factor things out, that's why those factoring things are kind of useful for us. So let's take a look and see how we can tackle this one, which is our last one. So I'm going to see, all right, so I'm going to take out a greatest common factor from here. It's going to be 4t squared. That's going to leave me t plus 2. In the denominator, I can take out a t, I guess. So that's going to leave me 3t squared plus 8t plus 4. I mean, it would be nice. I mean, I guess this t is going to cancel one of these out, but we must have a restriction. So t cannot be equal to 0, okay, because we don't want the denominator equal to 0. So that's 1. And, well, let's try to factor this whole thing out. So how do we factor this out? Well, I'm going to try to use decomposition because I notice it's a quadratic there. So this 8, so notice it's going to multiply 3 times 4. So multiplication is going to have to equal 12. And then addition or subtraction, I guess is going to have to be equal to 8. And I'm just thinking, I guess 2, so is it going to be 2 and 6? That's probably going to work for us. And we can add those up. All right, and 2 times 6 is indeed 12. So let's decompose this. So 3t squared plus, I'm going to put the 6t, so it goes with the 3 plus 2t plus 4. And so 3t. Okay, So that's going to give us our t plus 2. 2 and then t plus 2. So that means, so in total, what we will have, so this equals 4t, t plus 2, divided by t. And now, so this entire thing factored out. So it's going to be t plus 2 and 3t plus 2. Okay, so that's what we have there. This one is squared. All right, so we have our restrictions. So t cannot be equal to 0. T cannot be equal to -2. So that's from right here. And then t cannot be equal to -2/3. And that's coming from this one right there. Okay, so those are going to be our restrictions. So we can create our domain, so we know that something kind of is happening there. Now, there's going to be actually quite a lot of factoring. So this one is gone with that. One of these is gone with this. And that's going to be 4t divided by 3t plus 2. All right, so that's what we're going to run into. And it looks like, so again, so this 3t plus 2, so it's going to be very kind of similar to this 1/t, and except it's going to be kind of shifted around for us. Okay, so let's try to graph this, and then we'll take a look and see, you know, how decimals handles these particular points. All right, so I'll do that for you. Okay, so there we have it. Okay, so that's the original one. Now I put p of x instead of p of t just to graph it there. And notice, so this the -2/3, so we can clearly see that happening. That's kind of our asymptote there. Now it looks like as t kind of gets bigger and bigger, it should approach 4/3. Okay, so that's what it looks like. It's going to be kind of approaching that particular direction that we have. So that's pretty neat. And then, so, you know, we run into problems at 0. So we should see basically, okay, so our graph is undefined as we go towards 0. And notice that's exactly what happens there. Okay, so it hits there undefined. That's what you see there. And then the other problem was at -2. So as we go in here, so notice if we're approaching this direction and we get to -2, boom, undefined again. Okay, and those were some examples of some rational functions as an introduction for you. And now you can hopefully see and appreciate the factoring out, so that A, you can find out where the denominator is 0, because if you can factor things out, then that's super useful. Now also don't forget, I mean, if you're dealing with quadratics, you can always use the quadratic formula. If you've forgotten it, put up a link up above there. But overall, that's what we do with these rational functions, and if the numerator and denominator are polynomials. All right, so I'm going to end it here. Thanks for watching. We'll see you in a future video. Bye, everybody.